Welcome back to AP Physics, Chapter 7, 27, 28 review. There are a lot of problems on the review. I'm not going to talk through all of them in their entirety, but I'm going to highlight bits and pieces of the ones where I think there will be more questions, and you can always email me with more questions. So number one, you've got a conductive wire of length L, cross-sectional area A, resistance of R, and you're changing a couple of things. You're tripling the radius and you're tripling the length, and you want to know by what factor your resistance changes. You can reason mathematically through in your head, okay, or you can set up the problem and solve it down. What I do in the ones like these is I look for what is constant. In this case, pretty much everything is changing except it's the same substance. And so you have the same rho value. So if I take our R equals rho L over A and I solve it down for rho, so then basically rho before and rho after are equal to each other, and I end up with this being a constant. Didn't mean to write over the letters there. There we go. That's constant before and after. So I use that to be able to set up a proportion. Okay. Initially, finally, RA over L are the same. And then it's a matter of plugging in the specifics. 1 before you started and 2 after you finished making the changes. And then doing the math, lots of stuff will divide out to solve down for the factor by which the resistance changed. Part B, it's a straightforward plug into the R equals rho L over A for the values given. In number 2, you have a length of wire, 6 meters long, diameter of 1.2 millimeters. Make sure you convert your millimeters. It's made of iron and the resistivity is given there. You're calculating a whole bunch of different things as you go along there. I'm going to skip all the way down to part F, where you're calculating what the drift velocity is. So I have the equation I equals NQ V sub dA. Remember what your different symbols are. Okay, N is the number of charge carriers per volume. Q is the charge of each carrier, which in this case would be an electron. V sub d is your drift velocity, and A is your cross-sectional area. So we can solve that equation down. V sub d equals I over NQA. Most of the stuff in there we know, except for small n. So then over here on the side, I'm doing some work to be able to find n. Small n is the total number of carriers per volume, or capital N over the volume. Now, we can use a mole for capital N, but we have to have something to plug in for that volume. Okay, so I'm using the density equation. Density is mass over volume. And if we solve that down for volume, volume is going to be mass over density. And that's where what I'm plugging in right here is mass over density for volume. Then doing a little bit of algebra to invert, so then I've got capital N times the density over the mass. So then if I plug in a mole, 6.02 times 10 to the 23rd electrons, okay, then the mass I need on the bottom down here, that's the molar mass of iron. Periodic table, you can get that. Convert it from grams into kilograms, okay, and then the density of iron was given in the problem, and actually the molar mass was also. And so it's just a matter of plugging in. We get 8.52 times 10 to the 28th carriers per volume, and that's what goes in for small n in the equation below. Everything else we know, and you can solve down for the drift velocity. Remember, drift velocities are small numbers, and so our value we get here is a number times 10 to the negative 7th meters. They're always going to be reasonably small numbers. Number 3, you've got a 9 volt 7 watt radio turned on 9 p.m. to 2 a.m. Calculating a number of different things here. This one should be pretty self-explanatory, so I'm going to leave you to look at the work there. Number 4, you're given an equation for charge, and you want the current, or how much charge is passed after 2 seconds, and then the current, and when the current is equal to 0. This is just getting you used to dealing with a changing charge. And so Q of t to calculate the charge at 2 seconds, that's just plugging in 2 seconds. B, the current, dq dt. So once we take that, we get a current equation. And then in C, when the current is equal to 0, just set that equation from B equal to 0 and solve down for the time period. 5 and 6, more complex circuits. 5, pretty much drawn in a way that you can tell what's series and parallel. You have a predominantly series circuit because of R1, R2, and R5. And then you have immersed in there a little parallel of R3 and R4. So then to get the equivalent resistance, you're going to combine R3 and R4 with the inverse equation. 1 over R equals 1 over 4 plus 1 over 6. And that gives you a 2.4. And then you have the 5, the 7, the 2.4, and the 8 in series. And those resistors will all add together to give you the 22.4 ohms. Calculate then the total current. That's an EMF over R, 24 volts over the 22.4 ohms to give 1.07 amps. Then fill in anything that's constant. That current value that we got of 1.07 amps, that's going to go through R1, R2. It's going to split up in 3 and 4, but it's going to come back together to go through 5. So all of those that I've marked are 1.07 amps. So then you have enough to find any of the voltages of those 3 that you need to using V equals I times R. That just leaves us with resistor 3 and 4. And the 1.07 amps would go through there if there was only one resistor, which would be the 2.4. So then 1.07 amps times 2.4 ohms gives us the number of volts on each side here. And that's basically what I've done right there. And so then that tells us that there are 2.57 volts across that side of the parallel and 2.57 volts across this side of the parallel. So then V equals IR, you can calculate how much current goes along each side of the branch. Number 6, a little bit more complicated. I'm going to try in as much room as I have down here to smash in a redrawing of this. My 2 9-volt batteries in parallel will leave us with effectively a 9 volt. So each one is really only working half as hard, okay, because the charge can either go to the one on the right or the one on the left, and so these batteries will last longer putting them in parallel. Now, when we come out of that battery, the first thing we run into is R1, and that immediately tells us we have a series circuit. From there, from the right side of R1, we can get to R2 or R3 on wires. So I'm going to split twice. And I run into 2 resistors there, an R2 and then an R3. Following R3, we split again. Sorry, this is so small. Okay, and we get to R4 and R5. After that, our wire from R2 joins back up, and we run into R6, and then we come back to the battery. So that would be R6 there. So then you can see, hopefully, R1 and R6 are in series with the bigger parallel network, and the parallel network is a parallel of a single resistor, and then the right side of that is 3 resistors. 2 are in parallel, the 4 and 5 are in parallel, and that parallel is in series with R3. Now, finding things from there, I've drawn on the diagram above, starting with the little parallel of R4 and R5. Okay, that's going to be a 1 over 24 and a 1 over 8 equals 1 over R. Solving that down, we get 6 ohms there. We have then the 4 and the 6 in series, which gives us a 10 ohm of resistance. That 10 ohm and the 5 ohm are then in parallel. Doing the inverse equation, okay, we get a 10/3 or a 3.33, and then that 3.33 is in series with R1 and R6, and all those add together to give us 12.33 ohms. Calculating the total current, that's V over R, or the EMF over R, 9 volts over the 12.33 amps, or sorry, 12.33 ohms. That gives us 0.73 amps of total current. So then immediately fill in anything you can. That current is going to pass in its entirety through R1 and through R6. And so we can use V equals IR to calculate those voltages if we need those. That current then splits up across the whole rest of the parallel, okay? But we can still use the equivalent resistance of the whole parallel, 3.33, okay, and that current 0.73 amps to calculate the volts across the parallel. And so doing that, that gives us 2.43 volts. And I've done that right here to get that 2.43 volts. So then we know 2.43 volts is across each of those branches in the larger parallel. So then down below, there's 2.43 volts across that, and there's 2.43 volts across all of this. Okay, then it's a matter of, in the left-hand branch with R2, V equals IR. You can get the current through that. In the right-hand branch, V over R, but the R you have to use is everything in that right-hand branch, and then the volts is 2.43 volts. So that would be 2.43 volts over 10 ohms, and that gives you the current in that right-hand branch. And then everything else, once you have that current value, should then follow. So that takes us on to number 7. I've redrawn it there. Basically, you have almost parallel, but R1 makes it a series circuit. So you have R1 in series with everything else that is parallel. Okay, the 3 resistors in the very bottom branch drawn are all in series. Even though they're on different sides, they're still on one path. Okay, I equivalent, you're dealing with the series here, adding those up to get a single resistance value, and then that is in parallel with the rest of them. I've broken it up in my work down here for some reason. You could do it all in one. I don't know why I broke it up, but I did. So you could do it all in one to be able to find that equivalent resistance of 3.16 ohms. And once you've got the 3.16 ohms, that's in series with the 8, and so they add together. And so it's going to be 11.18 ohms. I total, that's going to be Ohm's law, EMF over R, 24 volts over 11.16 ohms to give you 2.15 amps. That 2.15 amps will pass in its entirety through R1, but then it'll split through everything else. Okay, so knowing I1, we can use that to be able to calculate V1. So V1 is 17.2 volts. Now, from there, probably what I would do, 24 total volts from your batteries because they are in series. And you've already accounted for 17.2 volts. Subtract. Okay, and what's left over is going to be how many volts you have through there. So that should be 6.8 volts. So then on our parallel, I'm going to have, I'm just debating the easiest way to be able to draw this. 6.8 volts across everything in that branch, 6.8 volts across everything in this branch, and 6.8 volts across everything in that branch. That is not saying that each of the individual resistors have 6.8 volts, but that's saying the voltage is broken up across the various resistors in a given branch, just like using the analogy of a battery as an elevator and resistors are stairs going back down stairs. Sometimes those stairs are broken up into different flights. So the 3 and the 10, that would be like 7 steps, then a landing, 3 steps, then the bottom floor. Okay, R4, all the steps are together. And then in the bottom branch, you have 6 steps landing, 5 steps landing, 9 steps landing. Okay, so you have various different sets of steps there by analogy. Once you have those voltages across each branch, V over R for the branch will allow you to be able to calculate what the, V equals IR, I times R. Let's see, what am I trying to find here? I2. I2 and I3 are equal to each other. And so that's going to be V over R for the branch, 6.8 volts, divided by 10 ohms. Okay. Likewise, in the other branches, when you go down to I4, that's V over R for the branch, 6.79 volts, divided by the 6 ohms. And V7, likewise, V7, we have to calculate the current first. And so the current in that is going to be the 6.8 volts divided by the 20 ohms, which is 0.34 amps. And then that 0.34 amps multiplied by 9 ohms to give you your equivalent resistance or your total voltage. Sorry, I've been making a lot of videos. Now, moving on to number 8, which is Kirchhoff's law. So we have the circuit drawn there. I'm going to emphasize a little bit more the way I've drawn the currents. If you're pondering the batteries, 12-volt battery would dominate. And so then I followed that and I drew I1 in the top branch that way. And then I2 across this center branch, and then I3 around here. From there, it's a matter of setting up your equations. Junction rule on that junction there. I1 enters that junction. I2 and I3 exit that junction. So then I1 is equal to I2 plus I3. So that's your junction rule. On your loop rules, okay, I'm starting at the upper left corner and going clockwise around on both of those. So then when I hit the 3 ohm resistor, so I'm going from here around to there. When I hit the 3 ohm resistor, we are moving clockwise, so we're moving in the direction of I1. So then that's going to be a decrease. So it'll be a negative 3 times I1. Then we hit I2, or the 2 ohm resistor, likewise, decrease, negative 2 I1. Rounding then through, so we've gone here and now we're hitting the 5 ohm resistor in the middle. We're going in the direction of I2. So that would be a negative 5 I2. Again, these are all I times R's. I hit the battery in the middle here, going from negative terminal to positive terminal, so that's an increase of 6. And then around there, I hit the 12. That is also an increase then of 12, and your total is equal to 0. Okay, on the bottom loop, starting at the point right there and going clockwise, I hit the 6-volt battery, positive terminal to negative terminal, so that's going to be a decrease. We hit the 5 ohm resistor. We're moving clockwise. The current is going opposite to that, so then we're going to hit an increase, positive 5I2. We round, we go down, we go across to the 4. We're moving in the direction of I3. So in the direction of I3, that's going to be a decrease, negative 4I3. We hit the battery, positive terminal to negative terminal. That's going to be a decrease. So that's negative 3 volts. And then we've completed the circuit. So you've got your 3 equations right there, right here, and right there. I did some algebra. So solve these down in your calculator. I did the algebra to be able to solve down for the various and assorted different currents. And lo and behold, we actually managed to set up the nearly impossible. Current I1 and I2 are 1.8 amps. And based on what we set up, 0 amps will go through I3. Couldn't do that again in a million years. But we managed to do it on that circuit. Number 9, RC circuit. So you've got a switch there, and you've got a couple of different resistors, but they are in series, and they are all on the same path with the capacitor. So then the time constant when we close to A is just R times C with the total of those 2 resistors in series. So 5.4 seconds. Okay. In B, when we close the switch to A, we want to know that initial current, which would be the maximum. The current will surge because there are no charges on the plates of the capacitor. Now keep in mind, 0 charge flows across the capacitor. So charges are flowing out and stopping, okay, at the plates of the capacitor, but energy is being dissipated along the way by the resistors. So EMF over R, 8 volts over 900,000 ohms, gives you that initial or maximum current. C, you want to know the current at 1.5 seconds. That's a straight plug into the equation. D, the maximum charge, C equals Q over V. You get the maximum charge if you plug in the EMF of the battery into that. E, fully charged, and you throw the switch to B. Now, using your discharging equation, keeping in mind here, okay, that Q that we wrote in the original equation, C times V or C times EMF, and it's straightforward, plug into there then. At 2 time constants, the exponent of base E just becomes a -2. And then at F, we want to know the voltage across the capacitor at 1.2 seconds. We can use our equation C equals Q over V, okay, but we need to know what the Q is, so that's a matter of plugging into the Q equation a time of 1.2 seconds, and the rest of our values, solving down for Q, and then plugging it into C equals Q over V.